Hello everyone, welcome back to a tech community. I hope all of you are doing great, right? एकदम जी जान लगा के मस्त तरीके से हाफ ईयरली एग्जाम के लिए प्रिपरेशन ले रहे हो, right? Very good. So today we are going to learn in this session about the complex number part 2. So already we have covered complex number part 1 in the previous video. जो बच्चे इस वीडियो में नए जुड़ रहे हो उन बच्चे से मेरा रिक्वेस्ट है, फर्स्ट गो थ्रू द प्रीवियस वीडियो, दैट विल बी हेल्पफुल फॉर यू. Okay, and you will be getting the video link in the description box. Okay, आज के सेशन में हम लोग कॉम्प्लेक्स नंबर पूरा खत्म कर लेंगे एंड नेक्स्ट सेशन में we will be discussing about the all the PYQs of last 5 to 7 years of this entire chapter. Okay, so let's get started. So before starting, we just need to make a quick recap of whatever we have learned in complex number. First of all, we have learned that up to grade 10, we have learned real numbers, but we need complex number because in order to solve a quadratic equation where we will be getting the discriminant is negative, in that case, we will not be able to find out root over of d because root over of negative terms, we don't know how to get it, right? For that, we have assumed that root over of negative 1 is an imaginary number, which is iota. Okay, and iota is denoted by I. So any number that consists of this I is basically called as complex number. Okay, so if there is root over of -5, I will say that this is nothing but root over of 5 times root over of -1, which is nothing but root over of 5i. Clear? Now, as I was saying that any number basically can be represented as a complex number. Okay, so how we will represent a complex number in standard form or in Cartesian form? Z will denote any complex number, and this can be represented as x plus iy or a plus iv form. Okay, now where x and y are the real numbers and I is the imaginary number. Okay, now this x is called the real part or denoted by real z, and y is called the imaginary part and denoted by imz. Okay, also what we have learned that if y becomes 0, then this term is not present there, so z will become x, which is purely real number. Okay, on the other hand, if x becomes 0, then it will become purely imaginary number. Also we have learned about that root over of minus a times root over of minus b is equals to minus root over of ab. Okay, besides also we have learned about the different properties of addition, subtraction, multiplication and division of complex numbers. Okay, like closure properties, commutative properties, associative properties. Also what we have done that what is the additive identity, multiplicative identity, additive inverse, multiplicative inverse, right? While doing multiplicative inverse, we have also seen that we cannot have in the denominator, we cannot have any I वाला term. I वाला term कभी भी नहीं रह सकता. Then what we can do in those cases, we need to multiply the numerator as well as the denominator by some number. Okay, now if it is purely imaginary number, let's say 1 over 2i. Okay, if the number is 1 over 2i, in that case, so it is purely imaginary number, then in the denominator we can see the purely imaginary number. In that case, we just need to multiply both the numerator and denominator by I. But if we are getting a number which is complex number but not purely imaginary, okay, let's say a plus ib, then we need to multiply both the numerator and denominator by a minus ib. And this a minus ib term is basically called as the conjugate of the z. Okay, conjugate of the complex number. If z is equals to a plus iv, its conjugate will be a minus iv. Clear? We just need to change the sign of the imaginary part, not the real part. Real part will be always real. Okay, it will not be changed. रियल लोग हमेशा सही रहता है, ठीक है, उस वो लोगों को चेंज नहीं कर सकते, इमेजिनरी लोगों को चेंज कर सकते. ठीक है, इमेजिनेशन हमारा बदल सकता है. क्लियर? नेक्स्ट इज, सो इतना तक हम लोग ने पढ़े थे. आज हम लोग क्या करेंगे, फिर यहाँ से स्टार्ट करेंगे. That is, most of the identities like a plus b whole square, a plus b whole cube, a minus b whole cube, a minus b whole square, a square minus b square, and many others which are valid for real numbers are valid for the complex numbers as well. Okay, for example, let's say Let's take an example. Let's say this question, write 6 minus 2i whole cube in the standard form. Standard form means x plus iy form, right? So if you see this, you can see that this is nothing but a minus b whole cube, right? And you know the formula of a minus b whole cube, right? Which is a cube minus 3a square b plus 3ab square minus b cube, right? Now here a is equals to 6 and b is equals to 2i. So 6 minus 2i whole cube. If I put the values, a value is 6, so 6 cube minus 3 times a square is 6 square multiplied by b is 2i plus 3 times a is again 6 and b square will become 2i whole square. Okay, minus b cube, that is 2i whole cube. Clear? Next, 6 cube will give you 216 minus, here you can see 3 to the 6, so 6 into 6 square will give you 6 cube again, so 216i plus, here you can see 2 square is 4, 4 multiplied by 6 3 is 18, which will give you 72, 72i square, and here you will be getting minus 2 whole cube, that is 8 and I cube. Okay, now just put the values, 216 minus 216i. Now since I square is minus 1, so it will become minus 72. 72 times minus 1 is minus 72. Okay, and I cube is minus I, so it will become minus 8 into minus I, which will give you plus 8i. Understood? So if you will be solving this, you will be getting 216 minus 72, which is 144, then minus 216 plus 8i, which will give you minus 208i. Clear? So this is your standard form. You can see that x is nothing but 144 and y is nothing but minus 208. Clear? If they would ask you the real part and the imaginary part, you can directly say that. Okay? I hope it's clear. Let's move on to the next question then. Next question is saying, not next question basically, equality of complex numbers. That means if two complex numbers are equal, let's say z1 is equals to z2. Okay, let's say z1 is equals to z2 and z1 is nothing but a plus ib and z2 is nothing but x plus iy. If we do that, we can compare the real parts as well as the imaginary parts. The real parts will be equal as well as the imaginary parts will be equal. So a will be equals to x and b will be equals to y. Clear? Two complex numbers are equal, that means their real parts are equal as well as the imaginary parts are also equal. Okay, now let's apply this in some question. Let's say find the real numbers x and y if x minus iy times 3 plus 5y is the conjugate of minus 6 plus 24i. How we can solve this particular question, let's see. Okay, so let's assign x minus iy times 3 plus 5y is z1. Okay, let's say that this is z1. z1 is equals to x minus iy times 3 plus 5y, and z2 is basically minus 6 minus 24i. Okay, now from here what we can see, if we multiply this, let's make this in the standard form. If we multiply, I will be getting 3x plus 5iy, sorry, 5ix minus 3iy, then minus 5y I square, right? Now I square is minus 1, so it will become 3x plus 5ix minus 3iy plus 5y. Minus 1 into minus will give you plus, so plus 5y. If you take the real parts together, you will be getting 3x plus 5y plus, if you take I common, you will be getting 5x minus 3y. I hope it's clear so far. Okay. On the other hand, z2 is given as minus 6 minus 24i. it has been given that this value z1 is basically the conjugate of z2. Let's find out the conjugate of z2 na. Conjugate of z2 is nothing but z2 bar, which is minus 6. As I said that the real part will be as it is, will be changing the sign of the imaginary part. So it will become plus 24i. Okay. So z1 will be equals to z2 bar, right? Since z1 is equals to z2 bar, we can say that 3x plus 5y plus I times 5x minus 3y will be equals to minus 6 plus 24i. So far clear, I hope, right? Now if we compare, I'll be getting that the real parts are basically 3x plus 5y and minus 6. So if we equate the real parts, I'll be getting 3x plus 5y is equals to minus 6. On the other hand, 5x minus 3y imaginary part will be equals to 24. So 5x minus 3y is equals to 24. Clear? Now let's solve this. If we will be solving this, what I will be getting? See, we have learned several types of solutions, right? For linear equation in two variables, substitution method, elimination method, cross multiplication method, you can apply any one of them. I am applying cross multiplication, elimination method over here. Okay. If we multiply, let's say this is equation number 1 and this is equation number 2. If we multiply the first equation, suppose I am trying to eliminate the y terms. Okay, that's why I am multiplying the first term by 3, first equation by 3 and the second equation by 5. If I multiply, what I will be getting? I will be getting from the first equation 9x plus 15y is equals to minus 18. On the other hand, 5 5 is 25x minus 15y is equals to 120. Okay, now if we add them up, I will be getting 15y will get cancelled out. 25 plus 9 is 34, right? 25 plus 9 is 34. So 34x is equals to 120 minus 18, which is 102. Okay. So if we solve this, I will be getting x is equals to 102 over 34. 34 3s are 102. So x is equals to 3. X is equals to 3. Now let's put the value of x in this equation. So 3 in the equation number 1, let's say 3 times 3 plus 5y is equals to minus 6. So 9 plus 5y is equals to minus 6. So 5y will be equals to minus 9 minus 6, which is minus 15. So y will be equals to minus 3. Clear? So we are getting x is equals to 3 and y is equals to minus 3. And that will be my final answer. Is it clear? I hope it's clear, right? If it's not clear, please pause the video and check it again. It will be clear. Okay, let's move on. Let's do this question. Z1 is given as 2 minus I and Z2 is given as minus 2 plus I. You need to find out real part of Z1 Z2 by Z1 bar and imaginary part of 1 by Z1 times Z1 bar. Okay, I will be explaining and you will be doing the second one by yourself. This is your homework and you will be saying the homework in the chat. Okay, so let's say z1 is equals to 2 minus I and z2 is equals to minus 2 plus I. So first we need to find out z1 z2. Okay, first of all, z1 bar. What is z1 bar? Z1 bar will be 2 plus I, right? Just we'll be changing the sign of the imaginary part. And what is z1 dot z2? Let's see. Z1 dot z2 is 2 minus I times minus 2 plus I. Okay, if I will be solving this, 2 times minus 2 will give you minus 4. 2 times I will give you 2i. Minus I times minus 2 will give you plus 2i. And minus I times minus plus I will give you minus I square. Now minus I square is plus 1, right? Because I square is minus 1. So minus of minus 1 will give you plus 1. So minus 4 plus 1 will give you minus 3. And over here you will be getting plus 2i is equals to 4i. Okay. and z1 bar you have already got as 2 plus I. So you are getting z1 z2 over z1 bar is nothing but minus 3 plus 4I over 2 plus I. Clear? Now, as I said, we cannot have any I wala term in the denominator. So what we need to do? We need to multiply by conjugate. What is the conjugate of 2 plus I? It will be 2 minus I. Let's multiply by 2 minus I. Okay? If we will be multiplying, in the denominator we will be getting 2 square, a plus b into a minus b. So a square minus b square. 2 square is 4 minus I square. In the numerator, what we will be getting? Check. In the numerator, if we multiply minus 3 times 2, I will be getting minus 6. Then minus 3 times minus I will give you plus 3I. 4I times 2 will give you plus 8I. And 4I times minus I will give you minus 4I square, which is plus 4. Okay. So minus 6 plus 4. If you will be solving this, you will be getting minus 2 over here. Plus 3I plus 8I will give you 11I over 4 plus 1, that is 5. Now, if you want to write it in the standard form, you will be getting minus 2 over 5 plus I times 11 over 5. You need to find out the real part. So, real part of z1, z2 over z1 bar will be nothing but this minus 2 over 5. Okay, this term. And that will be my answer. Clear? This is my final answer. You'll have to do the second one, imaginary part. Okay, imaginary 1 by z1 into z1 bar. You will have to find out that. Okay, this is your home task. Please finish it off and tell me what will be the imaginary part. Okay, tell me in the comment box. I'll check the comment box of each and everyone. Okay, let's move on. Now we have learned about complex number. We have seen that standard form of complex number is in a Cartesian present, right? What is the Cartesian form? Now, Cartesian form means it should be represented in Cartesian plane, right? How we can represent this in Cartesian plane? See, if we consider that x is denoting, the x-axis is denoting the real z, as you have already assumed that x is nothing but real z and y is basically imaginary z. So I am considering y-axis as imaginary z. So any point px comma y will basically denote the z, actual complex number z is equals to x plus iy. Clear? Where this OA distance is x and OB distance or PA distance is y. Okay. Now from here, if we want to find out what is the distance of this point from this origin, how we can find out? We will be joining this, and we know using Pythagoras we can find out easily that this is nothing but root over of x square plus y square. For a right angle triangle, hypotenuse is nothing but the perpendicular square plus base square. Okay. This value is called as mod of z or modulus of z or the absolute value of z. Okay. So mod z is nothing but modulus of z or absolute value of the complex number. Okay. I hope it's clear. All right. Let's move on then. So how we can calculate mod z? We can calculate mod z by doing real z square plus imaginary z square, because real z is your x and imaginary z is your y, right? Let's So if someone asks you what is modulus, modulus of the distance of the point from the origin, nothing else. Okay. Let's do one question from here. Z1 is given 2 minus I and Z2 is given as 1 plus I. What you need to find out? You need to find out the value of mod of Z1 plus Z2 by, Z1 plus Z2 plus 1 over Z1 minus Z2 plus 1. So let's calculate Z1 plus Z2 plus 1 and Z1 minus Z2 plus 1 separately. Okay. So let's do Z1 plus Z2 plus 1 first. Z1 is 2 minus I plus Z2 is 1 plus I plus 1 was there. So if we add them up, 2 plus 1 will give you 4 and minus I plus I will get cancelled out, right? So Z1 plus Z2 is nothing but 4. Let's do z1 minus z2 plus 1. If we want to do z1 minus z2 plus 1, what we will be getting? 2 minus I minus of 1 plus I plus 1. Okay, which will give you 2 minus 1, which is 1 plus 1, that is 2 ultimately. Then minus I, which is minus 2I. I hope it's clear. This calculation is clear. Now, let's find out the mod of z1 plus z2 plus 1 over z1 minus z2 plus 1. Okay, how we can find out this? See, let's put the values first. z1 plus z2 plus 1, we have already got, that's 4. And here you are getting as 2 minus 2I, right? Now you can take 2 from the 2 common from the denominator. You'll be getting 4 over 2 common 1 minus I mod, obviously. So 2 will be cancelled out. You will be left with 2 over 1 minus I. Now you already know that we cannot have any 1 minus I or 1 plus I, any I wala term in the denominator. So in order to erase this denominator's I wala term, what you need to do, you need to multiply the numerator as well as the denominator by the conjugate. So 2 will be multiplied with 1 plus I, because 1 minus I will be multiplied with its conjugate 1 plus I. Okay. Now 1 minus I times 1 plus I will give you 1 minus I square, right? 1 minus I square, which is 1 plus 1. Here you will be getting 2 times 1 plus I. Now 1 plus 1 is 2. So 2 times 1 plus I over 2. You can cancel this out. So basically your entire sum is nothing but you need to find out mod of 1 plus I. Here you can see the real value of z is 1 and imaginary value is 1 as well. So it will become root over of 1 square plus 1 square, which is nothing but root over of 2, and that's your final answer. I hope it's clear, right? Okay, that's great. Let's move on to the next part. Properties of modulus. Now we'll be learning few properties of modulus, and these are very much important for us. Okay, we need to memorize these properties. We need to see the proofs of these properties or check the properties whether they are actually valid or not. Okay, and we need to apply these properties as well. Okay, let's see. First one is mod z is equals to 0 when z is equals to 0. Why? Because let's say z is equals to a plus ib. Okay, in that case mod z will be nothing but root over of a square plus b square, right? Now mod z becomes 0, that means a square plus b square will be equal to 0. Now sum of the square of two numbers will be equal to 0 if individually the numbers is 0, right? So a and b should be equal to 0. So this is our first property. Clear? Let's move on to the next property. The next property is saying mod of z1 times z2 is equals to mod of z1 times mod of z2. Okay. Similarly, mod of z1 plus z2 or z1 minus z2, we can say that mod of z1 plus mod of z2. Division also we can say mod of z1 by z2 is equals to mod of z1 by mod of z2. Okay. You can write another property, mod of z1 plus minus z2 plus or minus whatever. It will be mod of z1 plus minus mod of z2. Okay. You can take z1 is equals to a plus ib and z2 is equals to x plus iy, and you can put the values, you will be getting the same answer. Okay, you can check them. Next is mod z whole bar, mod z bar is equals to mod z. That means if you will try to find out the z mod of modulus of the conjugate, it will be equals to the modulus of the original complex number itself. How we can prove that? Let's see. Let's say that z is equals to a plus ib. Okay, if I consider that z is equals to a plus ib, then z bar will be nothing but a minus ib, right? Then what will be mod z? From here we can say that mod z will be root over of a square plus b square, right? And from here we can say that mod of z bar will be equals to root over of a square plus minus b whole square, right? Instead of b, here it is minus b. But minus b whole square itself will give you plus b square only, right? Negative term squared will give you positive number only. So you can see z mod of z is equals to mod of z bar, which is equals to root over of a square plus b square. Okay. Next one is z times z bar is equals to mod z whole square. This is also very much important. Okay, you need to focus on this. How we can prove this? See, again I am saying z is equals to a plus ib. So z bar will be a minus ib, right? If I want to find out z times z bar, I will be getting a plus ib times a minus ib. Okay. Now a times a, we can see that here a plus b times a minus b, which is a square minus b square. Which that, so a square minus, instead of b, I will be writing ib whole square. Okay, which will give me a square minus I square b square. Now we know I square is minus 1, so it will become a square plus b square. And mod z whole square is nothing but root over of a square plus b square whole square, which is equals to a square plus b square again. So LHS is equals to RHS. So this is also proved. Clear? Let's move on to the final one. Final property of today, that is, and it is very much important, mod z to the power n equal to mod z whole to the power n. Mod of z to the power n is equals to mod z whole to the power n. Clear? We will be applying this concept, this particular property in the next question. Let's see how. Find the value of 1 plus I whole to the power 10. So let's say 1 plus I is basically z. Okay, this is z. You can see that this is the complex number. Let's see, this is z. So z to the power 10 whole mod. As per the property, it should be mod z whole to the power 10. Now, mod z means what? Mod of 1 plus I. A few times back we did, na? Mod of 1 plus I is equals to root over of 1 square plus 1 square, which is root 2. So, mod of 1 plus I is equals to root 2 whole to the power 10. Root 2 whole to the power 10, which is nothing but 2 to the power 5. That is nothing but 32. Clear? So, my final answer will be 32. Clear? Let's move on to the next one then. The next one is saying, if alpha and beta are the different complex numbers with mod of beta is equals to 1, then find mod of beta minus alpha by 1 minus alpha beta. Okay. Now, how we can solve this particular question? Any idea? See here. There are several ways to solve this. Okay. First of all, what we can do over here, that we know that I am showing the easiest one. Okay. We know that modulus gets distributed, right? So mod of beta minus alpha over 1 minus mod of alpha bar into beta, we can write it as mod of beta minus alpha over mod of 1 minus alpha bar beta. Clear? Now we know that for difference also we can separate this mod of b minus mod of alpha, okay, by mod of 1 minus mod of alpha bar beta. Clear? Now mod of beta is already given as 1 minus mod of alpha I am keeping as it is. Here mod of 1 is nothing but 1 itself. Then minus mod of alpha bar beta, we can write it as mod of alpha bar times mod of beta. Okay. So from here what we can say, it is 1 minus mod of alpha, 1 minus mod of alpha over 1 minus. Now see, we have just learned that mod of z bar is equal to mod of z na. So mod of alpha bar is equals to mod of alpha, and mod of beta is given as 1. So in the numerator we are getting 1 minus mod of alpha In the denominator also we are getting 1 minus mod of alpha. We can cancel out them and we'll be getting this value is equals to 1. Easy, right? There are several methods that is shown in your books as well. Don't need to go through that like that. You can do and this method and you can solve it within 4 or 5 lines. Okay. So don't need to do the longer methods. Okay. Let's move on to the next one. The next concept is saying representation of complex conjugate. Complex numbers, we have learned that this will give you the mod z, and this is basically this p point will denote the z equal to x plus iy, right? Now, if I want to find out the reflection of this p point on this y-axis, on this x-axis, or real z, what we can see, the other part, the reflected point will be the image will be created at p dash point, right? Whose coordinate will be x minus y. Now, if I want to represent this x minus y, what we will see? We will see that it is nothing but x minus I times y, because it is y is in the imaginary part. That's why we are writing x minus iy. Clear? Which is nothing but my z bar, right? So basically from here what we can say? We can say that the complex conjugate is nothing but the reflected point or the image on the mirror when the mirror is basically the real jet or the x-axis. Okay, clear? If we try to find out the image of a point with respect to the real jet or with respect to the x-axis, in that case whatever point we will be getting, that is your complex conjugate. I hope it's clear. So let's see. So this is your real z and this is your conjugate z, complex conjugate z. Okay, this is your complex number, actual complex number, and this is your complex conjugate. Okay, now let's apply this. Clear? Let's apply the concept of complex conjugate. Let's say you have been given x plus iy is equals to a plus ib over a minus ib, and you need to prove x square plus y square is equals to 1. How we can prove this? So let's say that this is equation number 1. What I am doing, I am taking complex conjugate on both sides. I am taking complex conjugate on both sides. What we will be getting? X plus iy's conjugate will be x minus iy, and this will be a plus ib over a minus ib whole conjugate. Clear? Now we know that conjugates actually gets distributed. So a plus ib conjugate over a minus ib conjugate. Clear? X minus iy is equals to. So x minus iy will be equals to a plus ib's conjugate will be a minus ib, and a minus ib's conjugate will be a plus ib. Clear? And this is your equation number 2. Now if we multiply the equation number 1 with equation number 2, what I will be getting? X plus iy times x minus iy. That's equals to a plus ib over a minus ib times a minus ib by a plus ib. Clear? Now this a minus ib will get cancelled out. A plus ib will get cancelled out. So in the right hand side you are getting 1. In the left hand side you are getting a plus b into a minus b formula, which is a square minus b square. So x square minus iy whole square, and already you have learned that I square is minus 1, so it will become x square plus y square. So x square plus y square is equals to 1, which is our required proof. So this is proved. Clear? Very easy, right? So what we have learned in this class? We have learned about the representation of complex numbers, complex conjugates, modulus of a number, how, what is the representation of the modulus, how we can find out the modulus. Also we have learned that how to apply the properties of modulus. We have learned various properties of modulus, like mod of z1 times mod of z2, they will get distributed and all right. So that's all for today. In the next class, what we will be doing, we will be just trying to solve all the PYQs from all the parts of, like, it can be of CBSE, it can be of ICSC. We will try to solve all the questions of last 5 years from this particular chapter. Okay. So that's all for today. Thank you.